I guess we'll just see along the way. So question 1. We need to find the multiplicative inverse of A. We know how to actually find that using the determinant. So the determinant of A is AD minus BC. So if we have a matrix A, B, C, and D, which we do, we can multiply the two numbers on the main diagonal, so 4 minus 2, and then subtract the multiplication of the numbers that are off the main diagonal. And this particular number tells us if this matrix, the structure, has an inverse or not.
Don't slack off, Zeta. Important to stay focused.
So our determinant is 1. It's 9 subtract 8. So this does have an inverse. And if we want to find the inverse, we could do that by doing 1 over the determinant. And then we do some rearranging. So we're going to rearrange D and A, and we're going to negate B and negate C. This is the 2x2 quick formula to find the inverse. So 1 over the determinant is just 1. So all I really need to do is do a little bit of rearranging of my initial term. So I'm going to swap the 4 and the negative 2. And then I'm going to negate the 2 3's to get something like this. So we're going to scan and see if we can find this matrix. Definitely not the first couple. Looks like this is the one that we're looking for. Boom, here it is. That's going to be our multiplicative inverse. And if we wanted to, we could actually perform the multiplication. Inverse just means that when we multiply, we get back to something like the number 1. So if I did take A, which was 4 minus 2, 3, and negative 3, and multiplied by this new matrix that we found, we should get what we call the identity matrix, which is a matrix that acts like the number 1. It basically, when I multiply by the identity, it just returns back the matrix that I started with. So in this case, we should get negative 8 plus 9, which is 1. If I move over and do this multiplication, we should get 12 minus 12, which is 0. And then we can move down and perform our other two multiplications. Here we get negative 6 plus 6 for 0. And then our last multiplication would be here, which would be 9 take away 8. So we can see that indeed this multiplication of A by A inverse does give us what we call the identity matrix. So we know that this, well, effectively is the inverse, and this question is asking for the multiplicative inverse, which is why we've done this multiplication operation in between our two matrices. So I am happy with that. Looks like we are Gucci. So the determinant we know is the multiplication. Oh, my pen is getting all glitchy, so let's move into pen number 2. We know that the determinant is the multiplication of the main diagonal, subtract the multiplication of the other two numbers off of the main diagonal. We want this to be equal to negative 24. So this gives us negative 18 minus 2z is equal to negative 24. Or if we want, we could multiply everything. Well, maybe what we'll do is we'll just add 18 to both sides. So negative 24 plus 18, I think, is negative 6. Negative 6. And then we can divide both sides by negative 2, and we should get that z is equal to 3. So, question 3. Find the coefficients and 2x2 submatrices for finding the determinant of A by expanding along the first row. So we call this a cofactor expansion. And if we go along the first row, I do actually expect this determinant to be 0. I can kind of see right off the bat that row 1 and row 2 are equal to each other, so this determinant should be 0. This matrix will not have an inverse. But let's go ahead and write out our cofactor expansion anyway. What we need is we need to assign to each one of these numbers 2, 1, and 3, either a positive or negative 1. In the upper left corner, we always start with a positive 1. And then as we move one step either to the right or down, we alter our signs. So the 1 is going to have a negative sign associated with it, and this 3 will have a plus sign associated with it. So it kind of looks like a weird happy face, I guess. But we're going to have 2, -1, and 3. Those are going to be the coefficients of the cofactors that we need. And then what we need to do is we need to highlight the number we're working with. And we're going to cancel out the row and the column. And that's going to leave us with the leftover. These are called minors. And these determinants help us kind of, for big matrices, these smaller determinants help us actually calculate the true determinant of our matrix. So let's move over to the number 1. The minor here is 2, 3, 2, and 2. And then finally, we'll move over to 3, and we should have 2, 1, 2, and 2. So that's what we're looking at here. Just be mindful here that we may have to do a little bit of work, right? So each of these are 2 by 2 determinants. So for my students that are working on questions like this, if we are using a cofactor expansion, these 2 by 2s, you can use the kind of the diagonal method, the main diagonal, subtract the off diagonal to get the determinants of these 2 by 2 minors. So it looks like we have some determinant work here for question 4 and question 5. Question 5 looks not too bad. Question 4. So for question 4, it's a 3 by 3. I like doing the 3 by 3 quick method personally, where I take the first 2 columns, I rewrite them down, and then I calculate these 3 values and I add them. So 6 times -2 times 1, that is -12. And then we have -2 times 3 times 1, so -6. And then we have 8 times 8 times -2, so 64. That's -128. So those are the 3 that we add. And then we come back and we do the same thing. We just have to subtract these 3 numbers. So our first subtraction should be -16. So -2 times 8 times 1. So subtract -16. And then we subtract 6 times 3 times 2. So 18 times 2. Is that 36? -36. And then 8 times 2 times 1. That's going to be 16 again. So another subtraction of -16. And then we just want to add this all up and see where this goes. So -12 minus 6 minus 128 plus 16 plus 36 plus 16 gets us to -78. All right, pop quiz. Determinant is -78. Does this matrix have an inverse or not? So what do we think? Throw it up in the chat if you think you know. Does it have an inverse or not? And if you have no idea what's happening, you have a 50-50 chance. All right, question 5. This is a lower triangular matrix. We are going to go ahead and just multiply the numbers on the main diagonal. 8 times 7 times 2. So we need 56 times 2. That's 112. 112. Enigma is correct. Yes, question 4 will have an inverse. Congratulations on scoring the first QED point of the night.
Nicely integrated.
Of course, question 5, this matrix will also have an inverse because its determinant is not 0. So what is question 6 asking us to do? Suppose AX represents a system of 3 equations in 3 variables. if matrix A is given by this, solve for the vector x in the linear system. I see. So there's this thing that goes, if I have a system AX equals B, where B represents the constants of the system that I'm working with, then I can find the XYZ values by taking A inverse and multiplying by the vector that represents the constants. So in our case, we could say that X is equal to A inverse, which is 1, 0, negative 1, 4, 1, negative 3, negative 2, negative 2, 1. We can multiply it by the B that was given to us, which is up here. And this multiplication should give us the values of like x1, x2, and x3, or x, y, z, whatever the names of the three variables are. Can we do this mentally? That's the question. So we get negative 1. So we're going to look at this first multiplication, which is here. And we should get negative 1 plus 0 minus 4. And I'm just going to put the final answers over here on the left. So that should be negative 5. Next, we want to do the second multiplication, which is row 2 by that column. So this should be negative 4 plus 3 minus 12. Negative 16 plus 3. I think that's negative 13. And then we have one last multiplication, which is 2 minus 6 plus 4. That's 0, I think. So we should be able to do the same thing realistically for the second part here. We know that x should be equal to A inverse, which we know is 1, 0, negative 1, 4, 1, negative 3, negative 2, 1. And we can take negative 4, 0, negative 1 as our B vector and just do this multiplication. So again, we can go through this multiplication. This one shouldn't be too bad mentally. So negative 4 plus 1 is negative 3. We have negative 16 plus 3, negative 16 plus 3. And then we have 8 minus 1. So we should get 7 here for our last component. And then the last question here is, what is A times A inverse? Well, if the inverse exists, we know that this multiplication should be the identity matrix. In this case, since both A and A inverse are 3 by 3s, we should get the 3 by 3 identity. What is this? This is weird. So I started with the rectangle below and I transformed it by a linear transformation. Here's the resulting shape. Enter a possible value for the determinant of the matrix. All right, let's have a peek at this.
The area of the blob as a whole will also be scaled by that same single amount. This very special scaling factor, the factor by which a linear transformation changes, has to happen to any other square in the grid, no matter the size. This follows from the fact that grid lines remain parallel and evenly spaced. Then, any shape that's not a grid square can be approximated by grid squares pretty well, with arbitrarily good approximations if you use small enough grid squares. So, since the areas of all those tiny grid squares are being scaled by some single amount, the area of the blob as a whole will also be scaled by that same single amount. This very special scaling factor, the factor by which a linear transformation changes any area, is called the determinant of that transformation. I'll show how to compute the determinant of a transformation using its matrix later on in this video, but understanding what it represents is, trust me, much more important than the computation. For example, the determinant of a transformation would be 3 if that transformation increases the area of a region by a factor of 3. The determinant of a transformation would be 1/2 if it squishes down all areas by a factor of 1/2. And the determinant of a 2D transformation is 0 if it squishes all of space onto a line, or even onto a single point, since then the area of any region would become 0. That last example will prove to be pretty important. It means that checking if the determinant of a given matrix is 0 will give a way of computing whether or not the transformation associated with that matrix squishes everything into a smaller dimension. You'll see in the next few videos why this is.
Yeah, I like that. That's a really interesting concept. Let's pop back over here. So I think the idea that 3 blue, 1 brown is saying is if we can actually calculate the area of these two things, then the determinant tells me how that area has changed, right? So like the determinant becomes the factor by which I multiplied the first area to get to the second area. So we should be able to calculate the area of this first thing relatively simply by doing, it's just 2 times 4. This area is equal to 8. Now, the area of the second one might be a little bit more complicated. Yeah, here it is. The area of the parallelogram. Oh, have we done the cross product, though? Yeah, Lou, that's what I'm looking at. The magnitude of the cross product is going to be the area of the parallelogram, but I don't know if we've covered the cross product in our course or not. I don't remember seeing the cross product. Oh yeah, I see. So let's see. Now A and B lie in the plane. So yeah, the third components are 0, right? So using the rules for calculating this. So hence the area of the parallelogram is the absolute value of the determinant of the vectors. Okay, so instead we write the area of the parallelogram spanned by these two vectors as the determinant of, so the vectors actually go as in rows. Okay. I'm cool with that. We had these vectors, right? These vectors were -8 and 4, and we had -2 and 4, I think. -8 and 4 and 2 and 4. So this determinant should represent the area of the parallelogram spanned by these two vectors. So -8 minus -32. So 30, basically 32 take away 8, which is 24. So when we go to compare our two areas of 8 and 24, the only way to get from 8 to 24 is to multiply by 3. So the determinant of the linear transformation has to be 3. Okay, so I had totally forgot about that. I had totally forgot that you could create these two vectors, put them into a 2x2 matrix, find the determinant that gives me the area of the parallelogram spanned by the two vectors. So that's what this 24 is representing, the area spanned by our two vectors, the one in black and the one in purple. So the one in black is here, and the one in purple is here. And what we're doing to answer the overall question is we're comparing the area. We're looking at how much larger or smaller in a multiplicative way is the first area compared to the second area. So we went from an area of 8 to an area of 24 through the linear transformation E. My guess is that the determinant of that linear transformation has to be 3.